Good afternoon, everyone. I'm Afiz Odola, and I'm going to be presenting my MSc thesis on the effect of stearic acid and cowpea protein isolate addition on ternary complex formation in normal and high amylose mixed starch. Everybody would relate with me that starch in Africa is something very common to every one of us. In Nigeria, we have a variety of food which we make with starch. And basically, we have wheat, we have corn, we have potato, we have cassava. And just by rough machining that, you can get your starch. And starch has a lot of applications in the food industry and other industries too. For example, you can use it to produce food, in paper, in textile, adhesive, and medical field. But my research today is going to be focused on the food producing aspects of starch, and also we can see a little bit about what influence my research is going to have in the medical field. So, the background of the research, basically starch, normal made starch to start with, whenever you take in starch, something happens. And what is it? There is an increase in glycemic index. To break that down for people that are not in the science field, whenever you take starchy foods, you realize that the blood glucose increases. The rate at which any starchy food you take increases the blood glucose level. That rate is what we call glycemic index. And now, what we've realized over the years with starchy foods is that when you take starch, it tends to increase the blood glucose level because of the high glycemic index. Now, this is a problem because in Africa, we mostly eat starchy foods, particularly in the rural area or rural communities. Now, this is a challenge for food scientists to find a solution. What can we do to this? And to that, we've realized that we can use different methods to modify starch. And one of those is the conventional method, whereby you can do chemical modification or you use synthetic chemicals. This is another challenge. We are now moving to a world where people are getting more conscious of what they eat, and now we want to find a way to modify starch using natural means, and this is what we call green chemistry. Now, using green chemistry, we realize that you can add some specific food components to another food to change their functional properties. So, also in this research, I'm looking at high amylose mixed starch. High amylose mixed starch in industry is rarely used. Why? Because before you can gelatinize high amylose mixed starch, it takes a lot of energy, and that will cost the industry much more money. Now we have to look at that. How can we change the functional property of high amylose mixed starch such that you can reduce the gelatinization temperature? And if you're wondering what is gelatinization, it is that temperature by which you are able to melt your starch. How does starch melt? When you subject starch to heat in the absence of water, it tends to absorb the water. Then, after a while, it starts to break down. When it breaks down, then it gelatinizes. Now, this is what the research is looking at. Then, we are looking at the nutritional benefits of the research as well as the socioeconomic impact of the research. Now, a way by which this research is going to solve the two problems I mentioned earlier is through the formation of ternary complex. What is ternary complex? It's when you combine three food components at a time to bring about a change in the structural formation of starch. And in my own case, I'm using normal mixed starch, stearic acid, and cowpea protein isolate. For your information, the cowpea protein isolate was extracted by me using the alkaline method, but I won't be going into details about that. Just to take you a little bit about how it happens. How does stearic acid, cowpea protein isolate, and starch get to react? If you could see from the image I'm showing, that yellow strand you are seeing there is a stearic acid. If you're a little bit familiar with chemistry, when you have fatty acids, generally, they have a tail, aliphatic tail, and they have the hydrophilic edge. Now, starch has two components. We have the amylose and the amylopectin. In normal mixed starch, you have the amylose in high quantity and the amylopectin in lower quantity. The amylose is what is responsible for the gels you see in starch. Now, when you subject starch, when you cook starch, then what is mostly responsible for that gel you see is what we call amylose. And that is the amylose there because It's linearly chained, and then it makes it much more readily available for interaction. Now, the amylose component of starch is what reacts with the fatty acid, in my own case, stearic acid. Now, you have the aliphatic tail going deep inside the hélice of the amylose. Then the hydrophobic head of stearic acid, which is mostly the carboxylate group, is what comes to react with the part of protein. Proteins, for some part of protein like arginine, they are positively charged. Then when the carboxylate group come in contact with the positively charged part of protein, then you can see the link from stearic acid to protein, from starch to stearic acid to protein. This is what we call ternary structure. And what are the potential application of this ternary complex? You can use it for drug delivery. It has been shown in previous literature that ternary complex formation can help in delivering some hydrophobic components to the active sites. And the second aspect is resistant starch. I forgot to mention earlier, a way by which we can solve the problem of high glycemic index in people that eat starchy foods is by making the starch a little bit resistant. And how does it happen? It makes them less accessible to enzymes that digest starch. So, what are the gaps in literature and why do I want to do this? The first part is, in most of the research that has been conducted about ternary complex, they mostly use beta-lactoglobulin, wheat protein, and barley protein. But in my own case, I'm using cowpea protein isolate. And why is it different? The difference is the structure of cowpea protein isolate is different from the ones I've mentioned earlier. Cowpea protein are globulin, while the previous ones I mentioned, they are mostly other type of protein. And again, there is no report in literature to show the effect of cowpea protein isolate on amylose mid-starch. And also, I'm conducting long pacing of amylose mid-starch lipid protein ternary structure, which has never been reported in literature. And the first part is the ternary structure formation of amylose mid-starch, stearic acid, and cowpea protein isolate has never been done. And this is a way of modification that is new in my research. And generally, the investigation about the ternary complex formation is limited in literature. In fact, now I'm struggling to get previous literature to back up some of the facts I'm getting from my research. So the aim of the research is to determine the effect that stearic acid and cowpea protein isolate addition would have on the rheological property, structural, nutritional, and morphological property of normal and amylose mid-starch, with the aim of producing ternary complex for different industrial applications. So I characterized my raw material. The cowpea protein isolate has about 93.5% protein on dry bases, and the normal mid-starch has about 26% amylose and 74% amylopectin, while for the high amylose mid-starch, I have approximately 72% amylose and 27% amylopectin. And do not forget that I said that the rate at which you are able to gelatinate a starch will depend on the amylose content. And from here, you can see that the amylose content of high amylose mid-starch is much more than the normal mid-starch. So going forward, I'm going to be showing some of my results. For the normal mid-starch, because of time, I'm just going to talk a bit about the pasting properties of my treatments. So the first part we are seeing here is a short pasting curve of normal mid-starch at varying stearic acid concentration. What we did was we varied the concentration of the stearic acid as well as the protein, then eventually we brought the three components together to see what would be the effects. So the first part here, as you can see, is short pasting. On the x-axis, you're having the time. On the y, you're having the viscosity. And to remind you, viscosity is how jelly your substance are. Now, the temperature profile you can see there shows the viscosity with temperature over time. Now, if you can look at the control, where I'm labeling it as 0% stearic acid and 0% cowpea protein isolate. When you look at the curve towards the end, you see that it's higher than others. That shows how much jelly starch can be when you are cooling. Let me take you through this curve. Yeah, it's going to occur in other curves, but if you explain here, it will be clearer when we go forward. So now the temperature profile, you see that it goes forward a bit, then remains constant over time, then drops again. So the first one that goes up, it's your pasting temperature, and then we hold for a specific time, then we start to cool again. Now, during the process of increasing the temperature to 91 degrees C, before holding and dropping again, what we do here is we are kind of simulating what happens when you cook your starch at home. Now we're going to see in real time what is happening as you are eating, holding, and cooling. Now, at the cooling phase, I just want you to pay more attention to the cooling phase. As at the cooling phase, you see that the one with 0% stearic acid and 0% copy protein isolate has higher final viscosity. The final viscosity is what you experience at the end of cooling. Now, looking forward, you see that the one with 0.5% stearic acid tends to be a bit lower than the one with 2.5% stearic acid. The second part is where we start to add the stearic acid, copy protein isolate, sorry. Now, when you add copy protein isolate to starch, just like that, we see a very deep breakdown in viscosity. But what is much more important here is if you look at that place that has the red circle, you see a plateau viscosity there. And that is what is spectacular about it. Now, when you add copy protein isolate alone, we see nothing. But then when you add copy protein isolate and stearic acid, we see that a small dip there. Going forward, we increased the concentration to 15% stearic acid, and you could see that we are seeing the same thing. Now, what this is saying is that there is a particular reaction happening when you combine stearic acid and copy protein isolates with starch, normal maize starch. To explain that, we went ahead to do what we call DSC. Thermogram is a way of studying at the thermal property of a particular substance. Now we studied the thermal property of copy protein isolate alone, and we realized that at about 79.9 degrees C, the copy protein isolate start to melt. And looking at this, we look at that red circle, we trace it up to where you have the temperature profile. Then we see that that point is the temperature at which the copy protein isolate start to denature. So the denaturation now, what it caused was that when protein denatures, you tend to have, protein is a fold. Let's say you have something like this. This is protein. Now when you eat protein up, it starts to open up. Then the outside here, normally copy protein isolate is hydrophobic, meaning it attracts water. Then when you open it up, the inner part is hydrophobic. It hates water. Then when it opens up, the hydrophobic parts get exposed, and for the fact that you have all of them in a system, then the hydrophobic part pushes water away, then stops starch from absorbing water. So that is what is happening there. Then what we are yet to get now is what is the impact of stearic acid. Because when you add just protein, nothing is happening. Then we are looking at other experiments to see the structural property of this formation. So this is a table showing what is happening, and these are figures explaining what I've mentioned earlier. And to wrap up, I just want to break this down a bit so everybody can relate. Now, when you have starch and stearic acid alone, you see those big granules there, and you have your stearic acid. Then when you subject them to heat, the starch starts to swirl. When they swirl, they start to break down. Eventually, you have something we call amylose lipid complex. Then the starch and the stearic acid start to interact to form amylose lipid complex. And that is where you see the final viscosity of normal maize starch with stearic acid lower than just starch alone. And when you have starch and protein interaction together, like I mentioned earlier, proteins start to open up when you subject them to heat due to denaturation. Then they coat the surface of the starch and prevent them from absorbing water. If that happens, then your starch will probably have a low viscosity. And that comes to the end of my results. Then the question is, are we able to produce the ternary complex that we're looking for? Yeah, potentially we can say yes, because we could see that the combination of the three components is giving us something very different from others. That is to say that we have a potentially positive result. And also from the statistics that I was not able to show from the table, we could see that it's basically different significantly from others. Then from other experiments, we'll be able to say specifically that, yes, we were able to. Thank you so much.
Well done, Hafiz.
Thank you.
Even though I don't really have any knowledge of food science, the little I know about food, it was beginning to play out. And it is nice to always see food, especially when we are having serious discussions like this. But I have two questions. The first question is, in producing protein isolate.
Cowpea protein isolate.
Okay, cowpea protein isolate acid, right?
No.
Interaction.
Okay.
Okay, yeah. In producing this your new idea, like this your new product, like which machine is used in producing it? And have you tried to look at the cost of the machine and the maintenance cost? And if you've done that, don't you think it will maybe impact maybe the affordability of your new of this product? Then the second one is what is really the limitation of this your study? Like what are maybe the challenges perhaps of the adoption of this very wonderful product? So yeah.
Okay. Can I take the questions together? Okay, maybe.
Okay. In addition to the questions that he has just asked, just for interest's sake, you mentioned that HEMS is also applicable for drug delivery. In what field has this been applied? One of your publications for 2015?
Yeah, that's all.
All right, and then the second one, this will be my last, is according, you had a broad aim or a long aim. If you can decompose that into various objectives so that it becomes clear in terms of when you're going to do your, generate your data, it becomes clear in terms of the information that you are producing as well as aligning with what you intended to to get as your information, as well as how you went about getting that information. So if you can do that, that will also help a lot for your examiner in future.
Okay, thank you. Okay, to your first question, Tony, the question was what machine was used in the production of the whole thing. And I'm glad to tell you that this doesn't need any equipment or machine. And it's just a matter of reaction between one component and the other. But then what I can just say is, before you can bring these three components together, something has to be set right. And one of them is, how do you produce those raw material? Like I mentioned characterization the first time. Before you can produce a standard product, then you have to be sure that you want to do something that is replicatable. So now, all you have to do is get your raw material, like the cowpea protein isolate, to answer that part a bit. The only difficult thing about it is, how do you want to extract your isolate? Because there are different methods, and you have to take into consideration a lot of factors. So I would just say the know-how is the basic thing there, and basically the other thing is just bringing them together in a system. And for us, what we did was we pasted the three components at a time, although some research would do them one at a time, then one after the other, probably the starch first, then add another component, then add another component. But what we did was we added the 3 at a time, because that would lead to another kind of research. So we added the 3 at a time, then we pasted them, like cooking simulation kind of thing. Then when you get those, then it will freeze dried. So after freeze drying, you get a wholesome 3 components in one system that you can use for further analysis. And the second question was the limitation. Basically, I would just say that for most of us working in the lab, you could realize that sometimes you have to do one thing 1,000 times. So the limitation is you being able to be calm enough to do one thing again and again and again before you get what you're looking for. The good thing is you already have reports in literature in which gives you a kind of boundary. Then if you are here, you know you're out. Then if you are here, you know you're out. Then you have something to look forward to in terms of what you're looking for. So I hope that answers your question.
Yeah, very well.
Thank you. And okay, I think yours was more of a recommendation or advice, and I would just say that basically what we are looking at is in terms of the aim and objective. If we try to combine the rheological property, the thermal property, the morphological property, if we combine those 3 together, what we basically want to see is, are we able to produce ternary complex? Now, the ternary complex can be used for various applications, like I mentioned earlier. It serves as a resistant starch in a way, and also the structure gives the opportunity for you to use it to embed other food components into it. Now, you asked a question about ARMS being used as a drug delivery agent. Yeah, I did say that, but that is the page where I was showing the importance of ternary complex and what you can use them for. It's after you've been able to incorporate other components, like the stearic acid and amylase method. Definitely, what we've seen so far, I was not able to show that. We are able to reduce the gelatinization temperature of ARMS, and hopefully from that we can get ternary complex too. If we are able to, then ternary complex can be used for drug delivery. And literature has actually pointed to the fact that it has been used to, I can't remember the name, I think N-naphthol or something, a cancer drug. It has, ternary complex has been used to deliver that drug successfully. Yeah, thank you so much.